All right, for today's final session, we invited Professor Robert Lucas. He's currently a professor of neuroscience and GSK chair at the University of Manchester. He's one of the pioneers in the discovery of IPRGC mediated circadian entrainment. He authored and co-authored more than 100 papers in scientific journals. Professor Lucas will explain us how light acts on our body and affects our living patterns and the consequences. We'll learn why evening and nighttime lighting is especially important. Please welcome Professor Lucas. Hello, Rob.
Hi.
Welcome
Hi,
back
Elliot.
to Samsung LED webinar.
Thank you.
We had great feedback from the audience after the first webinar back in February, especially owing to your lecture. How's your research going on around light and biology? It seems that COVID situation didn't deter it at all, for I see a lot of papers still coming out of your research group at Manchester and your co-workers worldwide. So what's new with your research these days?
Yeah, I'm pleased to say COVID did derail us quite a lot, I'm afraid,
Really?
as it has everybody. But we've managed to be pretty productive, really, over the whole of it. And I suppose one of the things I'm very excited about at the moment is the work that we're doing, trying to understand how bright daytime light can impact our core circadian clock, the mechanism by which we generate these 24-hour rhythms, and the latest evidence that we have that it's fundamentally increasing the amplitude of that clock, and we're very excited to be following that up in future.
All right. So today we're going to talk about relaxing lighting solution. So it may refer to light at night in most cases, as you just mentioned, and may generally refer to the lighting environment that brings relaxation to the occupants of the space. Just as the beautiful pieces of the architectural lighting work that Sally presented the previous talk, you saw that, right?
Yeah, I did.
Yeah,
it's fantastic.
She's in fact using warm white LED from 22 to 2700 Kelvin for hotel rooms, lounges, and dining rooms, and other residential spaces where people take a rest and enjoy the relaxing moments. And I talked about an additional tuning knob that we can utilize to effectively lower the light-induced melatonin suppression without necessarily having to reduce the brightness too much or to make the CCT too warm. So I guess now we can learn from you how light influences our body and the consequences of the interactions and what the desirable lighting conditions are in the evening and nighttime through your lecture. Right? Shall we begin?
Yeah, that's. Thank you very much, Elio. So, yes, I hope that. Let me see if I can get this working. Yay, we're up and running. So, yeah, I think my presentation follows on very nicely from the two that we've already had today. So, in brief, I'm going to develop some of the themes that you raised, Elio, and about the ways in which light impacts our biology, and break it down a little bit to describe the two fundamental impacts of light at night on our biology. And think about some of the kind of unfortunate and unpredictable ways in which those phenomena interact with our access to artificial light, and how that ends up having potential consequences for health and performance, before finally ending on what I hope is a more optimistic note, saying, what can we do about it? How is what sort of actions can we take to ensure that our biology is supported? So, of course, what we have to start when we think about the biological effects of light, that our body is expecting a regular 24-hour rhythm of light and darkness associated with the rotation of the Earth upon its axis. And as I'm sure this audience is well aware, that kind of external 24-hour rhythm is reflected in our internal biology by an internal circadian clock, which exists in our brain and drives daily variations in all manner of actions properties of our physiological and behavioral states. So we can think about that in terms of a sleep-wake cycle. That's kind of the most obvious, but almost every aspect of our biology is having a 24-hour rhythm, whether we're aware of it or not, and it's driven by this circadian clock. Okay, so what then is the consequence of introducing light into that night, which is one of the great revolutions of the modern age, right? That we do have access to this light when we need it. And the first thing to say is that our internal biological clock relies on the light-dark cycle in order to make sure it's appropriately phased with external time. So introducing light at night is going to change the phasing of our circadian clock. So it has a direct effect on our circadian clock to reset it. And it does it in a really pretty intuitive way. So if you're exposed to light in the early part of the evening, if we anthropomorphize your circadian clock, the message that sends to the clock is that dusk has happened later than it thought it was going to happen, because it's still light, therefore it's daytime, it's expecting to be night. So dusk must have happened later. And so what the clock does then is it delays its phase. So it shifts to a later day, to later time. Conversely, if light is experienced more towards morning, for the clock, that's a signal that dawn is happening earlier than it expected it to happen, and therefore that it will advance its phase. So those two things, the delay and advance of the circadian clock when it's exposed to light at night, is a very, very fundamental aspect of our property of our circadian system. Okay, so that's one way in which light is going to be important for our biology. But there's another effect, which is it kind of bypasses the circadian clock to directly affect our physiology and behavior. And that is, if you like, an override switch of light, where our body interprets the presence of bright light as being an indicator that it's daytime. And so we reorganize our biology to that kind of daytime state. And we can see that in terms of a reduction in sleepiness, so we're more alert, but a variety of other things. And earlier, you showed some data in your presentation illustrating this effect. This is just some from my own lab in collaboration with Christian Kajochen's group in Basel, where we're tracking the development of sleepiness across an evening in a group of healthy humans. And what they're actually doing is watching movies. What we do is we change the light environment. So we start out with a low intensity light environment. We compare it with a higher intensity. Actually, the design's a little bit more complicated than that, but we don't need to worry about that for today. And you can just ask people how sleepy they are and score it on a scale of 1 to 8, from very awake to very sleepy. And in the red, where people are exposed to dim light, you can see that there's this natural progression of sleepiness as the evening goes on. We all experience that, right? But you can interrupt that by increasing the brightness of the screen that they're looking at. And then by the end of the evening, people are less sleepy than they would ordinarily be. And that, as you mentioned as well, Elio, has a correlation in an aspect of physiology, which is easy to measure. And that's the production of this hormone melatonin, which is produced only at nighttime, and naturally would build up over the course of the evening here in the red. And bright light can suppress that here. So we have less melatonin at the end of that evening than if we'd been viewing the dimmer light. Okay. So light at night then can have those two effects. It can change the phase of our circadian clock and drive us to a more daytime state, more alert, less ready for sleep. And Ellie, I think you in your talk made the comparison with the drug, and I think it's a good one, that we then have to think about light really as a drug that's having important effects on our biology. And like any drug, that can be good, right? We wish that at the moment we could experience jet lag, but hopefully sometime pandemic allowed, we will be able to again. And it's exposure to light which allows our clock to get over that jet lag and resynchronize to the right time. Maybe you're performing a task at night that you need to be very alert for. It's a good idea to have the light bright for that, to help out with that. But I want to move to talking about how those two fundamental properties of light at night interact with something that's totally new from our biology in the last, 150 years, which is access to artificial light on demand. So our ability to choose light and how that interacts with those fundamental properties of light from a biological perspective. And I want to get across the idea that this introduces some more or less unhelpful positive feedback loops in the whole system. Okay, so let's go back to our schematic of those two effects of light at night. And I want to talk first of all about that circadian effect of light, so changing the phase of the circadian clock. So imagine then that you are exposed to bright light in the evening, and that delays your circadian clock. Well, of course, we tend to expose ourselves to light and artificial light at the times when we're awake. So if we've delayed our clock today, it's much more likely that we're going to be feeling awake and wanting to turn the light on tomorrow because this phase of our circadian clock is being delayed. So that means that there's an inherent positive feedback loop here, which is the delay in your clock means that at that time tomorrow, you're more likely to have the lights on, which in turn is going to delay your clock, which means that you're going to have more lights on the day after. So I hope that's clear that the shift in the phase of our preferred sleep time, then our circadian rhythm, means that it's more likely you're going to consume light at that time tomorrow. Okay, which in turn is going to phase shift our clock. And we know that is a phenomenon, or we're pretty sure that's a phenomenon, because of some of the early work trying to understand the circadian rhythm in humans. So it was, in the second half of the 20th century, that people started really, really codifying the circadian rhythm in humans. And a lot of the work that was done involved bunker studies where people are taken in temporal isolation and just looked to see what happened, for example, to their sleep-wake cycles when they didn't have any external reference of time. And importantly, in those early studies, people had were able to control their own lighting. And what was reported was that humans did have circadian rhythms, but that the period of them was substantially longer than 24 hours, so more than 25 hours, which was quite surprising. Actually, more recent data has confirmed that humans' circadian period is much closer than 24 hours. And what's become clear is that when we're allowed to control our own light exposure in the absence of any external time cue, then the period of the human circadian rhythms becomes more divergent from 24 hours, probably because of this phenomenon where we're exposed to light, it shifts our clock, it makes it more likely that we're going to be exposed to light at that time tomorrow, which shifts our clock further. And we end up having this kind of divergence of our circadian rhythm from the true state, which should be close to 24 hours. Okay, so that's one sort of feedback loop. The other sort of feedback loop is that this override switch, which makes us feel less sleepy. And the reason for that is, again, what do we do when we're less sleepy? We tend to increase our light exposure. So we might be watching TV, we might be pottering around the house, we might be going out, whatever we're doing, it's going to be, when we're awake, we want to be exposed to light. So that means that feeling less sleepy increases our light exposure, which in turn makes us less sleepy, which increases our light exposure, which makes us less sleepy, makes us less sleepy, which increases our light exposure, and so on. And so we have this additional feedback loop. And so these two things come together to mean that exposure to light at night in itself increases the likelihood that we're going to be exposed to that light at night, which increases the disruptive effect. And I try to explain this, for example, to my teenage children, that they're on their phones late at night and they say, well, I'm not sleepy, Dad, I can't sleep. And of course, the reason for that is partly because that light is overriding their daytime, their natural propensity to feel sleepy at that time of night. And it's probably shifting their circadian clock, which means that the fact that they are exposed to that light becomes a sort of self-reinforcing problem. Okay. So why is that a problem? Well, what we predict from such an arrangement is that the availability of light at night should change the time of day at which we would naturally sleep. And knowing whether that's actually true for everybody out in the world, of course, is enormously difficult because there's nobody who isn't exposed to natural light, or it's very hard to find people who aren't exposed to artificial light, which is what we'd like to be able to compare. So take a group that are exposed to artificial light and a group that aren't, and what happens to their sleep pattern. And that's very difficult. There have been a few opportunities to make that comparison. I'm going to show a couple here. One of which is to look at pre-industrial people, so people who currently don't have access to artificial light. And this is work from Horacio de la Iglesia, who's at the University of Washington in the US, and was studying this population of people from Argentina, where it's a kind of an ethnic group where they're at the kind of cusp of industrialization or becoming exposed to the industrial world. And so you have some communities where they have electricity and some where they don't. And what Horacio has done here is look at their activity rhythms in those two groups as a function of clock time. And what you can see is that people with electricity tend to be active through the evening, much more so than those that don't, and tend to get up slightly later the following morning, which of course is a very intuitive kind of response. We tend to be, well, why don't we read a book in the evening or stay up talking to our friends if the lights are available? And that then shifts the phase of sleep during the day. We can also ask what happens to more usual members of industrial societies when you take away that light signal. And there've been a couple of studies, this is work from Ken Wright at the University of Colorado, looking at what happens when people, for example, go camping and don't have access to a natural light cycle. And again, it tends to be that people go to bed earlier under exposure to a natural light cycle. Right. So because of these mechanisms, it seems likely that at least the timing of sleep during the day is impacted by access to artificial light. Is that a problem? I guess it becomes a problem when you start to impose social constraints. So when the alarm clock goes off, because if there's a tendency to stay up late and the alarm clock is waking you up at 7 in the morning, then we'd expect then that to produce a situation where we should have reduced sleep access. And indeed, that really does seem to be the case. So this is the result of a large survey from Till Roneberg and colleagues at the University in Munich, just asking people about their sleep on work days and free days. And we can see that for throughout the working life, there's a substantial shorter sleep duration on work days than free days. This is such an obvious thing to say from our everyday life that almost seems not worth quantifying. On the other hand, if we think about it, it actually says something quite important, which is that we're not getting enough sleep on work days because if we were allowed, we'd want more sleep. Okay. And so it's very typical for people to get less sleep on work days than free days. And that's totally predicted based on what we think about artificial light, its impact on our biology. Another really important thing is the impact is not evenly distributed across the population. So obviously, post-retirement, the relationship between free and work days becomes more kind of academic. But also, we look here at young people; they have a massive difference in the amount of sleep that they need or that they get on free days compared to work days. So some people are very substantially affected by this, and therefore we'd expect it indicates that there's very widespread sleep deprivation in human societies. So I've said that light alters circadian phase and drives the daytime state, making us less sleepy, for example. And we have these positive feedback loops. The impact of that is that probably changes the circadian phase compared to what it would be if we didn't have artificial light. And also it reduces our sleep duration. Importantly, though, it doesn't change our fundamental biology. So access to light doesn't change the time of day at which we are expected to perform. So we're still, even though we might be staying up late at night, we still have to be good for that 9 o'clock lesson at school. And also it doesn't reduce our need for sleep. We still need sleep as much as ever, it just reduces our propensity to get that sleep. Meaning that there's a tendency for us to work and learn at the wrong circadian phase, and also a tendency for us to experience this sleep deficit when we're not getting enough sleep. Poor sleep in particular, has lots of potential detrimental effects. So if you look at other studies, we know that short duration sleep is associated with high blood pressure, cardiovascular problems, coronary heart disease, diabetes, and obesity. And sleep deprivation causes poor mood, lapses in attention, errors and accidents, reduced memory efficiency, particularly memory consolidation, poor academic performance, disruptions to metabolism and appetite, and the poor immune system. So that raises the question, to what extent, if any, does light at night impair public health, happiness, and performance? And again, I think it's very difficult to answer that with certainty, because again, we don't have the comparator group of people that aren't exposed to light at night. So we're looking then for ways in which we can get at this problem kind of tangentially. We can sort of guess at the answer rather than having a very definitive answer. So, for example, if you compare it with smoking, if you want to look at the extent to which smoking causes, for example, lung cancer, at least you have a group of people who don't smoke, and you could look at the incidence of lung cancer for them. For light at night, it's much more difficult. So one of the ways that people have addressed this is by looking at the extent to which they'd expect light at night to disrupt people's biology, and that differs between people. So one of those concepts is the concept of social jet lag, and that simply is the difference between the time of sleep on free versus work days. So the idea being that on work days you have imposed times when you can sleep, whereas on free days you can sleep when you want, to at least a large extent. And so the difference between that gives you an idea of under what sort of pressure you are under during work days in terms of your sleep and circadian rhythm. And there have been a number of associations of high social jet lag. So this is one data set showing that the greater your social jet lag, the more you're during work days sleeping at a time that's different from what your clock wants, the more likely you are to smoke. This looks at obesity. So if you look at body mass index, there's not a very strong association between body mass index and social jet lag. But if you concentrate on those people who are overweight or obese, then there is an association. So if you're overweight, you're more likely to be obese if you have a high social jet lag. So social jet lag correlates with smoking, overweight to obese transition. A related concept is one of chronotype, which is the preferred time of sleep. So in this concept, low numbers are people who want to go to bed early, and high numbers are people who want to stay up late. And generally, the people who want to stay up late you'd expect to be having kind of more pressure associated with this light at night phenomenon, because they're going to be experiencing all that light during the evening and into the night. And this is just one study showing a relationship in Dutch school students between academic performance and chronotype. So let's look at biology, for example, and the grade that they get, higher grade is better, is impacted or correlates with chronotype, so that later chronotypes have worse performance. And in this study, it was particularly with mathematical and scientific subjects. So that late chronotype is associated with poor academic performance. That could be to do with poor sleep, could be to do with learning and city exams at the wrong circadian time. Another concept which has been introduced is the idea of poor sleep behavior, which includes that sort of circadian rhythm and sleep disruption concept altogether. And this is a very topical paper based on the UK Biobank. So the UK Biobank is an incredible resource where 500,000 UK adults aged between were recruited in 2006 to have all of their medical data collected and available for analysis, basically. So people can look at that in lots of different ways. And they're elderly now, so this number is 55 is wrong. I think they're 70 to 84, something in that order. And in this study, the question was asked is, how does poor sleep behavior correlate with outcomes of COVID infection? And COVID morbidity, if you concentrate on the red symbols here, increases as we get the sleep behavior burden becomes greater. So you're more like, these UK biobank adults were more likely to die after a COVID diagnosis, the more disrupted their sleep was. All right, what can we do about it then? I think the most important thing we can do about it in a way is to be aware that these deleterious effects of sleep, and they're stored up for a later time, so we can't necessarily trust intuition. So again, the conversations that I have with my teenage children of, yeah, it's fine staying up late on a Saturday night and exposing yourself to light, but that's the reason you feel really tired the following Thursday, because everything's out of kilter and you're not sleeping when you should do. It's very hard to make that association. And then the other obvious thing is to minimize light consumption at night to the extent that we can. And this graph, Ellie already showed you, which just to simplify, is the relationship between biological effects of light and how bright that light is in terms of melanopic EDI. And so, just to give you an anchor point here, this is around the light intensity of sunrise in Manchester in the summertime. So it's quite interesting that those biological effects all occurring over the range of light intensities we should experience as twilight, which makes sense, right? Rather than daylight. And a couple of things to point out, which is that room light can be too much, can be eliciting these biological effects. And also that because of this relationship, wherever you are on this curve here, any reduction is worthwhile. So even if you can't get to total darkness, it's still worth reducing that light intensity. There's one other thing about that I do want to highlight, and that is that there could be very substantial differences between individuals in terms of the question of how much light is too much or how much light is going to disrupt your biology at night. And this is work from Andrew Phillips and his group in Australia, where they looked at just a bunch of 55 young adults and looked at the light intensity required to suppress melatonin. And you can see, this is on a log scale, that there are big inter-individual differences in the answer to that question. So the intensity for a 50% melatonin suppression varies from less than 10 to more than 1,000 lux, just in terms of across ordinary members of the population. So it's difficult to make one size fits all directions. Nonetheless, as Elio mentioned, Tim Brown and Ken Wright convened a workshop in Manchester in 2018, looking to answer that question, and we came up with some answers about the target levels of light exposure in terms of melanopic EDI that for people would want to look at, and that works out at about less than 10 lux melanopic EDI for evening work, and then ideally darkness, but definitely less than 1 while you're asleep. Okay, so I think I'll finish there. I hope I've persuaded you that light at night is biologically potent, and therefore it is important that we keep it in mind. It can shift our circadian clock, drives an awake state, and sets up these kind of feedback loops, which are an important component. That sleep deprivation and disrupted circadian phase is an expected outcome of those phenomena, and could have unfortunate effects, and that we can address this by targeting a maximum exposure to light in the evening where possible. Thank you very much.
Thank you very much for your lecture, Rob. Like I did with Sally after her talk, I'm going to ask a few questions that I prepared on behalf of the audience. So are you ready for the questions, Rob?
I certainly am.
Mm-hmm. Good, great. So let me start by asking this. Each individual responds differently. to the brightness of the evening light, as you actually quoted in your lecture. So, and there's a common trend of elderly people having less transparent yellow lenses. It could require brighter, cooler color temperature light for them to perform. However, maybe deleterious to the younger ones who share the same space with them. It is common in Korea, for example, for the grandparents to take care of their grandchildren, to help their children who are a working mom or working dad. How would you recommend them if you were asked about the best lighting solution for them?
Yeah, I imagine this, I mean, I'm no lighting designer, but I imagine this is a general kind of intractable problem where you need to find a lighting solution that fits everyone. So I just go back to the recommendations that we made here in this paper, this consensus document where we talked about what is the right kind of light level. And I want to raise a couple of things, sort of caveats that we put into that document. The first is that whatever target light exposure we're talking about for the sort of circadian biological health, we first do need to think about safety, like safe levels of lighting, and I think that's a really important thing for elderly people, right? The possibility of falls and accidents is much more damaging for them than it would be for a child. Bumps and bruises are a totally normal thing of childhood, but for elderly people, it's much more of a problem. So I would say that's something that obviously people need to keep a very close eye on. The other thing we said explicitly was that the advice we were giving was for healthy adults. We weren't talking about children or the elderly. And there are a couple of reasons for that. One of which is that it's much harder to know what the relationship between melanopic EDI and response is for those groups. So there's a suggestion, for example, that elderly people might be especially sensitive to light because they have a lower circadian amplitude. The other thing is that in any given environment, people are going, the exposure, the effect of melanopic EDI is going to differ for people of different age, and probably for just ordinarily across the population. But the age thing is important because, as you alluded to in terms of yellowing the lens, is that as we age, because our lens becomes less transmissible to light, we become progressively less sensitive, especially to shorter wavelength light. And what that means is that in any environment, children experience a higher melanopic EDI than we would, and much higher than, and again, higher again to very elderly people. And that's especially going to be the case for bluer and cooler lights. And so I guess I'd say it's worth, without having any particular direct stipulation for any particular circumstance, it's just worth keeping that in mind, that ideally, the bluer, cooler light is going to have a bigger effect on the children than it would on the older people.
I see. Yes. So in designing actually the residential lighting conditions, I mean, we should be, I think, pretty much mindful about choosing the brightness and the color temperature lighting, taking considerations of elderly people as well as the younger ones, sharing the same space. I think, we should be really mindful about this knowledge. I think it helps a lot for general public, not only the people in the lighting industry. All right. I think, you saw Sally's presentation previously, just a moment ago. So she talked about, the emotional experience of light there. So she's been practicing lighting design using warm colored dim light for the venues where people spend their evening and nighttime to improve their the inviting mood of the space. I mean, this is something that you actually recommended for evening and nighttime lighting. So, I'm kind of curious. The whole lighting industry has been doing the same thing indeed for a long time. And they didn't know the scientific background, the circadian entrainment of light back then, but they knew what they wanted just naturally, as Sally said. So it seems that what's good for visual comfort is also good for the non-visual benefit of less disturbance to the natural circadian rhythm. So do you think it is kind of correlation or causation? Do you know any evidence supporting that a low melanopic EDI or less alerting light may also promote the feeling of comfortness, directly or indirectly through human physiology? Any comment on this?
Yeah, I mean, I think that there's an answer to this which is kind of has a scientific basis, and then there's another which is kind of hand wavy and just a guess, really. And the one that has a scientific basis is this kind of override switch here, right, which we know is happening. So it's certainly possible that those brighter environments make us feel less sleepy and therefore less kind of restful, and that signal can totally be available from a lighting design perspective, right? As part of the mood that's created by lighting. That's definitely possible. And in that way, that dimmer, lower melanopic EDI light promotes a transition to sleepiness in the evening, which is the kind of thing we might be looking for. And then the other thing is just more kind of hand waving, I guess, is that there's that correlation where, that's the kind of light exposure where we're used to being restful and getting ready for bed and things like that, and so we make that correlation, that association.
I see. Well, so that's why people, especially the lighting designers, kind of follow the track to the proper lighting, pretty much proper lighting design without actually having to know the details of the melatonin secretion and the suppression by the light. That's quite interesting. All right, and also you mentioned about many health hazards that come from sleep deprivation and short duration of sleep. One most interesting consequence of poor sleep was the poor academic performance that you cited from Zerbini's work. I'm personally very interested in that. I can understand that poor sleep deteriorates memory function and negatively affects the concentration of the subjects in the study in the following days, probably. But at the same time, it can be also thought to be true that when you want to study more, you stay late at night and you get yourself better prepared for classes and exams in the following days. If you study 2 more hours, for example, at night, you may only remember half of what you studied because of insufficient sleep. But if you don't study and just sleep early, you don't even have anything to remember, right? So it may sound too simplified, but anyway, I've seen students or those who used to be a student scoring higher when they studied hard, and studying hard is generally associated with studying late. So how should I interpret Zerbini's work in this context?
Really interesting and good question. So I think the first thing to say about this study, as all of them, these are correlations rather than causations. We don't know. We can never know exactly why it is that this relationship exists. But we do know, as you mentioned in your question, really, that there's a time of day dependence to alertness, concentration, etc. So if you're trying to work at the wrong time, you're going to be much less efficient. And also, if that means that when you sit your exam, your clock is in the wrong phase with respect to the time you sit in the exam, then your performance will go down. We also know that poor sleep impairs memory, drives poor concentration, poor alertness. So, I mean, the way that I would think about this is that, of course, in some ways there's no substitute for hard work, right? But by the same token, working hard is not always the right answer. the obvious kind of analogy here is one of Aesop's fables, the North Wind and the Sun, which, as you remember, the North Wind and the Sun have a bet about who can get this traveler to the cloak off this traveler, and the North Wind blows and blows and blows and blows, and the traveler keeps the cloak on faster and faster and faster, and gets harder and harder to pull off, and the Sun, of course, comes out, and the traveler takes the cloak off of his own volition. And it's a bit like that, right? That you need to work clever. And I would never recommend someone staying up till 3 o'clock in the morning the night before an exam. I can't see this having anything other than a detrimental performance to their detrimental effect on their performance in that exam. So it's about having a regular working schedule leading up to the exam. As with everything, you can't. Working against your biology is always going to be much harder work than acknowledging that you have these fundamental biological tendencies and accounting for them in the way that you structure your life and your study.
Thank you very much, Rob. Actually, I want my daughter to listen to you directly about that, because she insists that if she study harder until very late at night, like 3 o'clock in the morning, and then the next day she might be able to take the exam better because she studied harder and longer. It doesn't happen that way eventually.
No, yeah.
Well, actually, I saw a similar question from the audience. There was one who actually posted questions quite enthusiastically. So the first question actually is answered by you already. That was about the influence of the light to our brain, making it emit certain types of hormones. And then, you all talked about the melatonin, which is actually secreted by the pineal gland in the brain. So I think the first question was answered. But the next question from the same person is like, okay, I'm gonna read that. So sleep is impacted by the amount of light exposure, and lack of sleep influences work performance. But why are there some people who perform better in the night and perform less during the day? It basically contradicts your biological need, right? That was the question. So it's quite similar to my daughter's argue with me.
Well, obviously, we're all individuals. We're all different, as Monty Python said, and certainly, there's variability across the population. And there may be people for whom their circadian clock is built so differently from the average that there'd be something very peculiar going on. But I think more than that, it's really that the ability to work and perform at night is a consequence of having artificial light. And my guess would be that those people who think they work better at night, if you took away the artificial light, they would be functioning at a much similar circadian or diurnal phase than the rest of us, right? Because of those feedback loops. So what they are people who have a very strong tendency for that artificial light to delay their circadian clock to keep them awake. And so they get into this thing where actually their circadian rhythm adopts a very different phase to the natural light dark cycle than it does for the majority of other people. And so they become, in essence, very, very strong night owls. And my guess, again, it's very hard to know, but my guess would be that in a time before artificial light, such a night owl existence would not really have been feasible. And so what they'd have been is much more, well, you can welcome to stay up all night, but there's no light, what you're going to be doing. So that it's a property really of this interaction between those effects of light on our biological clock and our ability to turn light on when we want it.
Yeah, we're actually destined to be supposed to use light at night as a member of modern society. So it's hard to avoid. But still there are like a certain type of people like night owls and early birds, and then a little bit of differences between those people. But still, I guess the common mechanism of human physiology is pretty much the same, right? So.
Yeah, so I think that there definitely would be a tendency. Well, definitely, my inclination is that there would be a tendency under any circumstance for some people to be more night owls and some people to be more early birds. But it's the availability of artificial light that allows that to become an extreme. So that instead of being up having a slight tendency to being up to staying up in the evening or waking up early in the morning, the fact that you can then impose a light cycle on that, which has those positive feedback things, makes these differences across the population much more extreme. There's not massively strong direct scientific evidence for that at the moment, but that's certainly something that we're interested in working on, and I think generally it feels likely.
I see. I guess there are also other elements that makes you, in some cases, perform better at night by isolating yourself from other disturbances that you get a lot during daytime. Probably that's something that we might consider. All right, good. Again, thank you very much for your lecture today. Your thoughtful research will help us to find the right way to use the light in today's lifestyle. As you said, using light improperly at night can lead to reduced sleep duration. We need that for some purposes. I mean, we really need to stay awake. Like myself, in Korea, it's about like 1 a.m. and I try to intentionally delay my circadian rhythm 1 hour per day, just like the lab rats that you used for your research. 1 hour a day is working pretty well. So I've been shifting my circadian rhythm 1 hour a day about 3 days. So I'm I'm so energized at this moment. So the positive feedback that you explained works pretty much well for me today.
Good.
Anyway, thank you very much again. And Rob, I hope really to see you again next time in other arrangements.
My pleasure.
All right. Thank you very much. Bye-bye, Rob.